The other thing that we were noticing, as I was saying before, was that mathematicians were being considered as dinosaurs because we didn't want to get away from what might be considered traditional teaching methods of lectures and exams and various other things. And Merrin in particular found that looking at the education literature, there's not a lot of voice for mathematics. A lot of the people that were writing in education are either social scientists or humanities or something in that area where there seems to be more of this trend away from more traditional forms of education. And certainly the people that were running the university at the time were in that camp. So what we wanted to do was give the mathematics voice in education literature, and we thought the best way to do that is let's go out and talk to a lot of maths educators. So this study is an ongoing study, and if any of you are interested in talking to me and being interviewed for this, I'd be more than happy to talk to you and get your ideas. But essentially there are 3 points in the interview. What should students gain from a maths education or from a mathematics course, subject, unit, module, whatever you call it at your local institution? How should they be taught? And how should they be assessed? And what we're looking at today is really just the answer to that question and the first 33 responses. And I think, Merrin, you'd agree that we've got a very rich data set from the people that we've interviewed so far.
Yeah, absolutely. It's amazing.
So we've probably got a couple more papers or maybe some PhDs or something will come out of it. So the interviewees that have taken part, that were in this analysis, and it was Merrin and Law who've done the analysis, obviously predominantly Australian and predominantly New South Wales, because that's where we were. We do have people from most of the states in Australia for this. 4 people from the UK and Ireland, 1 from Finland, 1 from South Africa, 1 from North America. 5 of the people were teaching stats only, 18 were maths only, and 10 were teaching both areas. Since then, we've added several more people, a few more Australians. We added a New Zealand interview yet? I know I've got one planned, and various other.
We've got 2 Kiwis, Don.
2 Kiwis, okay. So we're gradually building it up. And as I said, if you're interested in being interviewed, please let me know. Just drop me an email or talk to me today if you're here in the room. Essentially, the analysis has been thematic analysis, which unfortunately Claire's not here today, but we really got to know thematic analysis through Claire Mullen's work and a couple of papers that Anthony and I worked on during COVID. So the 6-phase approach. Merrin, do you want to talk to this? Because this has really been the work that you've done.
You know, you invited me along to watch you talk, Don.
Oh, I didn't. I invited you along to be part of the presentation because you've done the work a little bit.
It's been sprung on me. I'm not prepared. Sure. So the approach has been described by Bron and Clark. It is the one that Claire used. And so we referred a lot to her methodology as well as to the official work by Bron and Clark. It's a cyclical process where you go around in circles until you finally get to somewhere. So phase 1 is getting to know the data. So reading through the interview transcripts, listening to them, forming your own opinions, making your own summaries of them. And then opening them up and going through line by line and summarizing what's happening in each line and trying to get very succinct summaries called codes. And it's very interesting because I had before this was my first go at doing thematic analysis, and at first I thought, well, what's the point of going through every line because I'm already getting everything out of it when I summarize it. But it turned out that I wasn't, and you there's a lot of depth in there. There's a lot of things that people say that might not be their main point, but there's still things that they're saying that came out in the line by line analysis and coding. And what also happened is that you're going along, and then someone, in interview 4 or 5, someone would say something. You go, oh, yeah, actually, the earlier people said that as well. And you go back and recode and go around in circles until that stops happening. And then lined up all the codes and tried to put them into groups and then had a look at what sort of groups we came up with for the are we just talking mostly about the what did students gain on today?
Yeah.
Yeah, okay. Yeah, so for looking at what students should gain from their studies, it worked really nicely, just like the theory said it should. And the codes fell into a fairly small number of themes, which going around in circles and so on, we came up with, I think, 4 main themes and then a couple of sub themes that were specific only to subgroups. And then I assume Don's going on to talk about what we called the themes and how we interpret them.
Yeah. Yeah. Thanks, Mary. Please jump in if I miss anything or say something wrong. Yeah, so I mean, this was new. The first time I've been involved with this were the studies that we did with Claire during her PhD a few years ago. So it's something that's probably quite different to most of us that are in mathematics, but it's an interesting project. So the themes that came out of this as to what students should come away from a course with were these 4. So content mastery, which broke into 2 sub-themes, technical mastery and conceptual understanding, mathematical communication, mathematical thinking, and mathematical appreciation. And we'll break these down a little bit more and talk about them. And the other thing that we've done with this and with the paper that is forthcoming in IGMAS, which has been accepted for the special edition for the Delta conference that's being held in Brisbane later this year. We looked at it through a lens of teaching mathematics or teaching and learning mathematics now with AI. And how does that affect what we maybe should be doing or thinking about? By the way, if anyone has questions at any time, please jump in. I don't want this to be a lecture. I'd much rather a discussion. But to go a little more into the themes, content mastery broke into 2 areas. There's technical mastery, which is procedural things. So being able to invert a matrix, being able to integrate a function, differentiate a function, whatever it is at the particular level that you're working at. And the quotes here are from various people's interviews. Everybody that we interviewed mentioned, I think everybody mentioned technical mastery as being something that students should come away with. The majority of people also mentioned conceptual understanding. And there's nothing in this that's not, I think, probably blindingly obvious to all of us. So students should understand what they're doing and why. Mathematical thinking. Well, there's a good question about what is mathematical thinking anyway, but we took this as this idea of higher order thinking, selecting the correct methodology to approach a problem, critical thinking skills, critiquing solutions, being able to prove theorems, having problem-solving skills. And again, do you remember how many people cited this merit? Was it everybody?
No, I don't have a number off the top of my head. These 4 themes, the vast majority of people talk to though, and Don's presenting them in order. So basically everyone, I mean, it's not very deep that everyone said that students should master their content, but this one came in a close second.
Right. And we'll talk more about how that's taught, or how maybe that's taught currently, and how we're thinking it might change. Mathematical communication also came in fairly importantly, and both receptive language, being able to read mathematics, and expressive language, written, spoken, graphical, and demonstration of mathematics. I think in Australia, at least, that's being pushed quite hard at the moment. We, in a lot of institutions, use what are called board tutorials. So in a tutorial class, students will work at a whiteboard in groups of 3 or 4 students, solving a set of problems, usually unseen problems. So they've in theory, they're supposed to have done some work beforehand on problems, and then they come to the board tutorials and they work on these unseen problems in groups of 3 or 4. So they have to communicate, they have to be able to write mathematics, and the tutor walks around the room and discusses them, and they look at each other's work. I mean, you know, we encourage the group work in those things, but that's one of the main ways I think that we encourage mathematical communication. One thing that I've found, both Merrin and I found, we were both teaching at Western Sydney a unit called Maths for Engineers Preliminary, which was an introductory maths subject. And I put some questions into the tutorials there, which gave some of the hallucinations which the early versions of ChatGPT got, asked students to identify where's the first mistake, correct the answer. And a lot of students just couldn't do that. Or they'd look at, I'd take up some solutions that students had put into a class test that were wrong. And then we put those back to the students. In fact, I think one day we gave them a day to be the marker. And a lot of them couldn't identify the problems that were happening or what was wrong with a particular solution. So we assume that students can read maths, because I don't think that's something that we teach directly. And we assume they can read a textbook. But if there's something wrong in the textbook, are they going to recognise it? Or are they going to recognise good maths from bad? I think that's something that's important. And the fourth area was this area of mathematical appreciation. So appreciation of the presence and relevance of mathematics, its social history. Just maths for an interest in the beauty of mathematics and the interconnectedness of mathematics within subjects and mathematics with the outside world. And I think, again, most people agree that that's something that students should do, but I wonder sometimes if the way that we teach doesn't actually crush some of that. Again, we'll maybe talk more about that. Any questions or comments at this stage? Really interested to know if anybody has other major areas that you think perhaps should have been included.
You mentioned on the previous slide about critical thinking, or being able to spot a mistake.
Mm-hmm.
Under mathematical thinking, you also had the word critique. Was that also what you meant? Critique of solutions you have there.
Yeah. It comes into the mathematical communication thing as well. Yeah, and these themes don't exist in isolation. They're interconnected, and I'm going to come to what we think are the interconnections in a minute. But yeah, yes.
I think that is going to be important, being able to spot mistakes. Because AI, you could put everything into AI and it'll tell you an answer.
And it'll tell you confidently.
Yeah. And the question is, do our students accept it?
Absolutely. Yeah, I think that's a critical thing in where we're heading. Anything else? Yeah. Oh, you were just scratching. I just saw the arm go up. There are also some localized themes. Didn't quite make the final cut for the themes, but there are also things which were coming through the interviews. This change of students' mindset from schools, particularly with first-year lecturers. I'm not sure what it's like here in Ireland, but in Australia, I think a lot of high school teaching is done to the test. So it's when you see this problem, you apply this formula and you do it this way. And obviously, when they get to university, there's a shock to the system because we're suddenly asking them to think about what they should be doing, not just giving them a set of things to do. So that idea is something that we got quite a bit from first year students. Developing self-confidence and self-efficacy in maths, also from first year and support. We get a lot of anxious students coming into first year, certainly at Western Sydney, where they seem to be, the attitude seemed to be if you're vertical and breathing, we're happy to have you. The Maths for Engineers preliminary course that I was taking, the engineering department was taking students in who hadn't done maths since what's your lower level, year 10 in our system. Junior certificate. Okay, so they were accepting students with junior certificate, year 10 level maths, so no calculus, and then expecting them to jump into an engineering degree. And you get a lot of students that just, it blows their mind. So working on that is also a big thing that was certainly for the Australian people. And workplace skills, particularly the stats lecturers, are developing a lot of, development of workplace skills is important. That's probably harder in maths because we just don't know where people are going. I mean, in some sense, maths is a much broader area than statistics. If they're going into statistics, there's a set of techniques that they need to be able to use and software that they need to be able to use, and it will be similar in each workplace, where I think probably in maths that's not so much the case. Okay, so now to this point of connections, and this wasn't in the talk that I gave last week in Liverpool, so since we had time to expand, this is a large part of the paper we've written. So Miriam, please jump in along here as we go. So these again are the themes that we identified. The black arrows are things that we see as essential. So content mastery requires mathematical communication, but also mathematical communication requires content mastery. So there's a two-way street there. Mathematical thinking requires content mastery, but you can potentially think mathematically without really knowing all the theory. So you can have what we might call a logical
other way around, I think, Don, isn't it?
Other way. Is it?
Yeah. Yeah, you need content mastery. You need to know some content
mastery
stuff
for
before you can think mathematically.
True, yeah, sorry,
but
you
can turn the handle and pass your test without turning on your brain. Sadly.
Yes. So content mastery really required for everything. Again, no blinder there. Communication necessary for appreciation of mathematics, but you can appreciate mathematics without being able to speak deeply about it. We didn't see necessarily a link between mathematical thinking and appreciation of mathematics. We were thinking of this along the lines of, if that connection is there, or if that connection is not there, it's sort of like someone appreciating music. You can appreciate a Beethoven symphony without being a musician. But if you are a musician, you obviously have a deeper appreciation for what's going on. So,
sorry, these are all things you sort of, from the interviews, you sort of,
it's sort of from the interviews, and Merrin and I having a lot of conversations about how we thought this should all string together. I think there was some things came out of the interviews, wasn't there, Merrin, as well?
Yeah, it's this is what we came up with, like Don says, through what people said in the interviews. We didn't ask anyone, how do you relate these things, because the themes themselves came out, and a blend of, things that are said in the literature and so on. But I don't know that I'm not aware of anyone who's actually talked to this directly. So it is just it sort of reflects our thinking more than anything. As we're reflected on the interviews and the literature and our personal experiences.
Yeah. And the red arrow between computational skills and computational understanding is something that we'll talk more about. And really, I think that's the crux of where our paper is, because I think what we saw was a lot of people that we interviewed feel that the computational skills are essential for conceptual understanding. And so you grind away computational skills until the student gains conceptual understanding of whatever it is that they're playing. And we're not so sure that that's necessarily the case these days. And this is where the whole Gen AI thing comes in. I mean, as you said, you can plug almost any undergraduate maths tutorial problem into Gen AI, and it's probably going to get it right. Last semester, I was teaching Maths 1B at UNSW and Maths 1A, which are both calculus and linear algebra courses. I put all of the tutorial questions through Gen AI. Not only did it give me almost textbook answers to every question, it also gave me the LaTeX for them. So I didn't have to do a lot of work to generate my notes for the term. And if that's the case, why are we insisting on students doing so much of this? You know, should we be spending as much time as we do on computational skill just for the sake of computational skills? Now, a lot of the people that we talk to, of course, are teaching service maths. And I think one of the things that came through was that one of the reasons for teaching a lot of computational skills is that that's what whatever faculty they're teaching for expects their students to come out with. And maybe that's an old-fashioned view of looking at mathematics that we need to think about changing their minds about. So I had something else in mind I was just about to say about that.
It's a comment on that. But
Yeah.
I was thinking about this recently. I mean, if we say that, okay, nobody needs to know how to find the inverse of a matrix, then where are we going to be in 50 years' time? We're going to have a world where no human knows how to find the inverse of a matrix.
I agree with that.
We're going to type into the computer, it's going to tell us the answer. And
yeah, no, I'm not saying that we should remove computational skills, but I was talking to somebody in the UK initially who was interested in collaborating with this, but wasn't able to in the end for other reasons. And his comment was that he was bemoaning the fact that a tutor had spent an entire hour's tutorial working through the inverse of a 3x3 matrix with a class. You know, yes, you need to know how to do it. You need to know the techniques, and you need to have done it once or twice. But do you need to do 20 cases of it? And do you need to be able to invert a 4x4 or a 5x5 matrix? Or, you know, whereabouts do you stop? In Maths 1B, the Maths 1B course, we spent something like 2.5 weeks dealing with different techniques of integration. And I kind of thought, you know, all of these are really essentially doing the same thing, but we're not talking about what the underlying process of these techniques is of, you know, essentially manipulating function to something else that we can integrate. But we're just teaching these 25 different ways of integrating a function. Why? Yes, you need to know that those techniques exist and maybe more about what it is that's happening underneath. But 2.5 weeks of just doing that's, I think, crushing students' enjoyment of maths.
No, I agree with you that it makes no sense maybe to do 10 times the inverse of the matrix. But as Gary said, these things are made from us.
Yeah.
So I think we as mathematicians, but also as lecturers, we shouldn't forget that we are the human and these are machines that are needed to us. Mm-hmm. So referring to the inverse of matrix, in my opinion, it's important maybe to break down the solution in steps. So in this way, I'm not teaching a computational skills, but I'm training them to computational thinking. That is, in any case, a way to let them interact with the machine. Because if you think about the inverse of a matrix, you can break as an algorithm. So if the student understands the algorithm behind doing this, it makes no sense then to do the 4 and 5. And
Yeah.
so it's more how we teach instead of why
Yes.
we should teach.
Yes.
Because it's, you know, a way to train them to more higher level of computational thinking skills.
Yeah, no, that's entirely where I'm going with this, actually. So thank you. Maren, is there anything else we need to say about this?
Could I just
yeah.
ask Gary a question? For people who don't know, Gary was our head of school for a long time. And you would have had conversations with, say, service teaching departments like engineers, commerce, agriculture, and something like that. Do you have to make the argument often, or did you have to make the argument that, well, maths is going down this path, you know, data science is very in now, or AI is coming in, and we really need mathematicians to do this? Because financially speaking, I know they probably would. Some of them would like to teach it themselves, have a commerce person teaching maths for business or whatever it is. But without getting too political, are you allowed to say anything about having conversations with senior deans and stuff like that around why we need statisticians and mathematicians to teach this stuff?
I think we would. One of the answers I would give was that we're more up to date. By up to date, I mean this.
Yeah.
You know, so the mathematicians are more up to date with what's going on. We had meetings about, do you need to teach all the techniques of integration for 3 weeks, or when we can just plug it into Mathematica and get the answer? And maybe we should be more conceptual. And we did have those meetings with, say, engineers, and it was agreed that that's what we would do. So the kind of consensus was, no, we don't need to teach. We don't need to do the inverse of 4x4s and 5x5s, but we need to teach the method and the more conceptual. So they were happy with that.
Yeah.
But they're happy with mathematicians and statisticians doing that, because we're the ones who know that. We're the ones who know it better. And maybe I'm getting arrogant, but
Yeah.
we're the ones who know it.
Yeah, no, I think you're right. We're the ones who think more deeply about that, and
Yeah.
maybe you're ahead of the curve here, because I think without what we're seeing is that a lot of people need to have that sort of conversation. Sorry, Mary. Oh,
no, I don't know. I don't want to raise it because I know you said you talk more about sort of the link between procedural and conceptual. I look more at second level maths, but I can see a lot of parallel. People talk about, oh, well, they only know the procedures and how to do it, they don't know the conceptual. But equally, you can't teach the conceptual in a vacuum. And there is some research in that space in secondary that places you do need both, and they build on each other. And it's a bit like you can teach the underlying concept about matrices and inverse, but you do also need a certain amount of practice of doing it out on paper to cement that conceptual understanding. And so I don't think, and even going further down into use of calculators, but you still need to have the concept of how to add and multiply large numbers. Yes, you might in the future use a calculator for particularly large ones, but you need to have the underlying. It's like you need to do it by hand first before then you can use the tool.
Yeah.
And it's a bit like Gen AI. It's a tool.
Yeah.
But you need to have the understanding and be able to do things yourself first before you can then use the tool in an effective way.
Yeah, no, I totally agree with that. And the analogy with the calculator is something that I think I've mentioned in the abstract, or certainly in the paper, that what we see Gen AI being at the minute is, for those of us that are old enough to remember when calculators came in, probably only me. But yes, it's that same sort of revolution in teaching that's happening.
Yeah, I think you need to do enough calculation as well to actually understand it. If you just do it once, it's not there. So I think you need to do enough. Not saying you need to do it all the time, but I think you need to do enough to cement the.
Well, Mary gave a great presentation on this at FYI Maths a couple of years ago. The video's still on our YouTube site about students not having a mental model of the integers because they don't do enough hand calculation. So yeah, it's a balance. Maren, did you have anything else to chime in on here?
Yeah, I'm probably going to preempt what you're going to say, so apologies if I am. I had two things to say. The first is that at this point there was a divergence in the views of the statisticians and the mathematicians. The statisticians had gone pretty strongly to a model where they started out with conceptual big picture understanding, and then as the students progressed, they could dive into the computational stuff. But it was, at least at, in first year, and so it was outsourced to the computer. So they would talk big picture about, what's going on in this data set, what are we trying to understand from it, and then they'd let the computer do the hypothesis test and they'd interpret the meaning from that. And so they went in that way. Whereas for the mathematicians, the dominant view was definitely one of a straight line where you've got procedural skills up one end and you've got conceptual understanding up the other end. And precisely. And the problem is that you don't have a lot of time with the students. And so the question becomes one of where do you position yourself along this line so that they get enough computational mastery, but they also get enough time to understand things. And the debates all seem to be about that, where do I put my balance point on this linear scale? Because we all know that both of them are necessary. If you can only do procedures, then your existence is pointless because the computer can replace you. But you can't have conceptual understanding without some procedural mastery. You need enough mastery to be able to read mathematics, be fluent in the language, to get into more difficult concepts. You've got to be able to do the computational skills really fast, so you're not using up all your working memory just trying to do those calculations, etc., etc. And then, as we all know, doing things by hand is a way to help you understand things. So the debate is seems to be really centered about that. Where do we put our balance point? And obviously it's different for different cohorts. So that's what we got out of our interviews, and something that makes sense from our experience as well. That was everything I want to say, Don.
Okay.
I think that's fair enough for stats, because a lot of the calculations, if you want to calculate the variance of, that's a.
Yeah, who wants to do that by hand?
I know. I think it is sort of a different. I think that's probably part of the reason why that.
Yeah.
In elementary and second level education, in the literature, there was a taxonomy, Bloom's taxonomy of educational objectives. Yeah. I'm wondering, has it been updated? Does this fit into it somewhere, and so on?
I think there's several taxonomies out there. Again, Merrin, I defer to Merrin's skills in the educational area and knowledge of these things, but I think it is something that we considered. Merrin?
Yeah, it's really interesting how these things fit in. Bloom's is such a lovely taxonomy. It's not completely quite as simple as it makes out. A lot of the literature is sort of offering variations on a theme, but very crudely. Things like memorizing your facts is at a lower level of sophistication than creating your own mathematical theory. There's no doubt about that. And there are stages going up. So I guess you can frame that inside that framework and say, you have to know your facts, and you have to be able to apply those facts before you can really deeply understand the material and synthesize it and use it in new ways. So you can, and I think that's this linear model came out of cognitive theory rather than out of Bloom's taxonomy, but it's certainly symbiotic with it, I think.
I have a good friend in America who's a music educator, publishes a blog, and he's published a quote a few months ago. I should have got the exact wording of it, but essentially it said that a master teacher is someone who takes you to the landscape, shows you the landscape, but doesn't actually tell you what you need to look at. And in a lot of ways, I think as mathematics teachers, we tend to be the exact opposite of that. We're saying, look at that blade of grass, look at that blade of grass, look at that tree, look at that rock, look at that blade of grass. And the big picture gets lost because we're spending so much time on detail. And that kind of comes down to this finding the balance. Now, as we said, that's what came out of the interviews. But what we're proposing, or what we started thinking about, was mathematics, not so much this as computational mastery and conceptual understanding as being opposite ends of a spectrum, but really being intertwined. And we're thinking maybe, and this really is up for discussion, but mathematics being a more experimental subject, so that instead of students just doing a lot of exercises for the sake of doing exercises and learning the technique, we take an approach that's more like the approach in physics or chemistry, where students follow a designed experiment. So not the sort of thing that we're doing as professional mathematicians, where experiment 99 times the experiment fails before we actually get to the new theorem, but at least taking them through some sort of process where the exercises they're doing are framed in an experimental framework and build on existing concepts, but also give them a direction towards new understanding and new concepts. Merrin, do you want to add anything to that?
I guess an analogy is in chemistry. When you're studying wet chemistry, you don't go and do classes on how to measure things into beakers and whatever else have you. It's a necessary skill and you can't survive without it, but it's purely a means to an end. And you'll be doing an experiment to mix two chemicals and see what happens. But in order to do that, you have to master these procedural skills. And I guess our thinking was sort of like that. And part of it was to address not just the things that we're debating about how much should students look, but also the student perceptions, which are that mathematics is just about doing procedures and getting the right answer. And a lot of our teaching kind of doesn't really stop them from holding those views. So whereas if things are structured, so, we're going to do an experiment and we're going to, what was our example used in the paper, Don? It was something about matrices, wasn't it? It was
well,
yeah, okay. So if we want students to look at solution spaces of matrices or whatever, we do it explicitly. We'll say, okay, here's some theory, and look, here's all the different things that a determinant does for you in terms of your solution space, and now go away and practice and see what happens. Just practice until you get good at it. And that kind of that traditional approach, it reinforces the idea that what we're doing is we're doing something procedurally, and we just need to get to the right answer. It doesn't shake that up. Whereas if you structure it, say, more, I guess, even more constructivistly, you might say, so let's do an experiment. Let's investigate how the singularity of a matrix affects the solution set, and then you give them a set. So you don't tell them what the outcome is, but it's carefully set up so that they have a family of various matrices that show what they're meant to get out of it, and then they can draw their own conclusions and so on. But by structuring it as an experiment, then the procedural element of it, which is finding the determinant, is no longer the focus of the lesson. So we don't say, okay, everybody, here's how we go about finding a determinant. Now let's practice it. It's something like learning to measure things into your beaker. It's something you need to do to get to another point, but the focus is taken off it and the focus is put wholly on the understanding. Why we're doing this? We're doing this to understand the relationship between determinants and solution sets.
Another example, I think, of this is something that Jim Pettigrew, one of our colleagues, is working on at the minute. He's written up a simulation. It's 3x3 matrices again, but row reduction, 3x3 matrices. So it takes away all the calculation. The student puts in what the row operation is that they want to do, and the system automatically generates the next step. But alongside that, he also wrote up a part of it to graphically show the planes. So, 3x3 matrix is 3 planes.
What's this in? It's not numbers, is it?
No, well,
It's just Java.
JavaScript,
It's in Java.
JavaScript and JSX graph, but it could be adapted into numbers. But he started out just showing the initial planes, so you could see the point of intersection if you fiddled with it a bit. And then we were talking about it, and I said, well, why don't you show the planes at each step as you do the row reduction? And if you do the full Gauss-Jordan row reduction, what you're really ending up doing is you end up with 3 mutually orthogonal planes which intersect at the point of solution. And I hadn't really thought of the process as doing that geometrically before he started doing that. And then since then, he's taken that a couple of steps further of looking at the column space of the matrix and the solution as being the scalars that you multiply each of the column vectors to add together to get to the 0 vector or so. I don't remember the exact details, but it just built up to this very graphical sort of way of exploring something which is a pretty basic kind of computational thing that we normally teach. I think potentially students could get a lot more out of doing that than doing a dozen examples.
Yeah, because it's much more, I mean, they make mistakes with the minus, and that's really not what you want, is it?
Yeah.
You want that they know what the row reduction is.
Yeah. So
there we are again with conceptual versus technical skills.
Yeah.
Well, the problem there is that they're coming out of school. Those sort of technical skills should have down by the time they leave school. The mistakes they're making with negatives and negatives and stuff like that.
I was teaching them the maths for business people yesterday, the maths bit thing, and it was to multiply 2 fractions.
Mm-hmm.
And they did on the calculator, okay, but do I cross multiply?
And because they just learned an algorithm.
Yeah,
They learned an algorithm for division, and then they've forgotten which one was for which.
Yeah.
Instead of any sort of understanding as to what that
God help you when you have to teach them to add fractions.
Yeah.
Half plus a third is 2/5, isn't it? So I think, well, the look of things, our time is up. Just come back to this initial quote and think if maybe this is a direction. I'm not saying we're not saying it's the direction, but it's perhaps some food for thought, and I'd be really happy to talk to people about it and get opinions.
Can I just ask you what's the general profile of the interviewees?
We approached people who were mathematicians who were who were educators. So we weren't looking for people who
third level.
third level,
Third
yeah, university level. There's also been a couple, or at least one person who was nursing, numeracy education and nursing, several people in maths education, in maths support, but at the tertiary level. And we particularly focused on people who had an interest in mathematics and education. So we weren't looking at research mathematicians who possibly teach mathematics begrudgingly because they have to, or at people who are in education who have lots of theories that none of us can apply to anything. So it was people who are probably I hope like all of us in the room, I hope I haven't just offended someone, but people who have an interest in mathematics education and how it works at the tertiary level, but I think it has influence back to the secondary level as well.
And basically, we're interested in current best practice, not as is actually happening or as people imagine it to be happening. And so we were recruited through Sigma and through the Australian FYI Maths, and then through word of mouth.
Yeah, the person I interviewed from Finland, I found at ICME last year that felt it's someone that was interesting. So I think that's we're at the end.
Thanks very much, Dan.
And almost right on cue.
That's good for you online.
Yeah.
Forwarding.
I worked on a small project in a paper where we interviewed research mathematicians who were also teaching about their views on teaching and learning at math at both third level and at second level. Now ours were all based in Ireland. And it was interesting, there was a lot of overlap with what we found with what you were. So one of the things that jumped out for us was, and we kind of touched on it a little bit there, is what it means to be good at maths is very different at third level than at second level. In that, and you meant, at second level, even with concept, there is an element of teaching to the test. You have this high stakes test, and you want to be fast and accurate. Like that, the answer is important, and someone who's good at maths at second level tends to be, or is perceived to be good at maths at second level, is someone who gets the right answer quickly. And that then at third level, there's a complete shift. And that was one of the things that a lot of the mathematicians we spoke to came out, that they want the students, they don't care how, by getting there fast, or if they've made an arithmetic mistake along the way, they want to think about the process. And it's that conceptual understanding of why this algorithm works and so on. But all of the other themes were very similar to stuff that we could.
Something else I was going to say on the way through there, mathematical thinking. Like we tend to teach concepts, conceptual mathematics, and communication fairly directly. We don't teach mathematical thinking or appreciation very much in the subjects, and we haven't really delved into all of that analysis yet. Like that's only one of the three questions that we're asking. But my thinking is, and I think I've discussed this with Merrin as well, is that we tend to teach mathematical thought, not mathematical thinking. So we we give a theorem and its proof, and then exercises on that. We're sort of taking the nuggets without doing any of the digging to get to them, which is the thinking part.
Yeah.
And the experimental part would maybe start to redress that a little bit as well.
Yeah, I was going to comment on that experimental part. I think it's a great way to go. We're constrained by time.
Yes.
So I think that takes time. And we've got this syllabus that we have to get through in 24 lectures. And we have to get that. And so that works against spending time on, let's discover this theorem for ourselves.
Yeah, I look, I know, I agree with that, but there's a couple of things there. I don't think what we're suggesting is that we get students to discover a theorem for themselves. Maybe we point them towards it and then we give that result. So the experiment might point towards something else that's coming on. We're not going to expect them to find the theorem by themselves. So it's not that sort of discovery experimentation. And the other thing is that I think one of the main reasons for tertiary education is to create lifelong learners. So we say we need to get through all this content, but do we? Wouldn't we be better generating or getting students who had a much greater sense of curiosity because they've enjoyed what they're doing and want to go and explore this on their own? So that maybe some of the things that this is back to the blade of grass. Should we not be showing them a little more of the big picture and getting them to think a little more for themselves? Don't know. Again, I'm just throwing that, we're just throwing that out there.
Just to ask, what percentage of an age cohort or, a first year or second year cohort would be going into the service areas where they're using mathematics as you described as service mathematics? What percentage of the first years or the second years would be?
That's a really good question. I mean, at UNSW, we have a reasonably...
Oh, yeah, perfect, yeah.
UNSW, we have a reasonably large maths program, but like Western Sydney, it would be 95% of students were service teaching. I think that depends on the university very much. Let's keep the things in the chat here. Okay,
I think that's true largely. Certainly here, 95% of students we teach more are not going to be mathematicians, but they're going to go finish and go out there in the world and do various things. And I think the math appreciation part is very important.
Yeah,
with them, because it's an impact. It's our greatest impact that we have is with those 95% of our students who go out to the world and do lots of different things, and if they can appreciate mathematics, we're.
The other 5% have already been convinced.
Yeah.
Well, I said if they're doing a maths degree, they presumably appreciate the mathematics. But yeah. Any other comments or disagreement or other ways of thinking about doing this? Because we're open.
Just on the linear, not a question or comment, just on the linear algebra stuff you were talking about, the geometrical approach to the raw reductions. I know they do a lot of that in States. But again, they've got 16, 17 semesters in States. You know, they can afford the time, and they've got these extra classes with the kind of workshops, a bit like your board tutorials. They might have, 16, 17 weeks, they might have 4 hours of content, then an hour of workshop. That's 16, 17 weeks. It's just, we're in a sprint. I mean, week 1 and week 12 are kind of gone for us. It's week 1 is here's the door, week 12 is we have to do a revision. Well, 10 weeks.
Yeah, UNSW, we have 10-week terms with a 1-week break in the middle.
Right.
Now we only have 1 hour of tutorials, but we have about 4 or 5 hours of lectures in our first year sections.
In Trinity, I've only got 10 hours for my first year. 10 weeks.
Yeah.
My first year. We're a luxury here with 12 weeks.
Yeah.
But even if we could provide some of these things as resources so that we could maybe encourage students to want to, again, it's this idea of encouraging students and developing the appreciation that they might want to do some of that as part of the time that they're supposed to be studying by themselves. It might